In this video, we're going to be proving the law of cosines, which we see written here. So what we're going to be doing is showing how each of these three equations is developed from an acute triangle, which is what we'll look at in case 1. Case 2, we'll look at the obtuse, and in case 3, we'll talk about what happens in a right triangle. So with that in mind, we're going to start straight into our acute triangle case. In this case, we have an acute triangle ABC with side lengths AB and C opposite their respective angles. And there's two things that we need to do here to this diagram. We're going to add a couple of altitudes into it. So the first altitude I want to add, we're going to call it H1, is going to be from point B down to segment AC. So that's H1. Now we notice that H1 divides that opposite side, segment AC, divides it into two parts. So we're going to call this distance from A to the foot of H1, we're going to call that X, which means this other length can be referred to as B minus X. Now there's a couple of things then that we can do with those two smaller right triangles. First things first, because our three expressions or these equations deal with the cosine of the angles, let's look at the cosine of angle A and the cosine of angle C as they appear in these little right triangles. So in that case, the cosine of angle A would become X over C. If we multiply both sides by C, C times the cosine of angle A is the length of X. Using angle C, the cosine of angle C, in that case, the adjacent B minus X over the hypotenuse in that right triangle, which is A. All right, so we're going to multiply both sides by that denominator A and then rearrange some terms to get X isolated. Okay, so these values of X that we now have are going to come into play again in a little bit. Let's go back to the diagram though for a moment. You may notice that in each of these equations, they're pretty similar to the Pythagorean theorem in structure, especially this last one, c squared equals a squared plus b squared. This adjustment is what keeps it from being the Pythagorean theorem. And that's the part that actually does come from the fact that we have two right triangles here. So if we use the Pythagorean theorem in this case, we've got a couple of things that we can write. We could write for this right triangle that x squared plus the length of H1 squared is equal to c squared. And in this right triangle, the one on the right, the quantity b minus x squared plus H1 squared is equal to a squared. Okay, so what we want to do, we now have a system of equations, two equations with two unknowns, and we need to somehow rewrite these equations in terms of only the angle measures or the side lengths of the original triangle. In other words, we need to get rid of these x's and h1s that we currently have. The way that we're going to do that is by using elimination first. We're going to take this first equation and subtract from it everything in the second equation, which means when we subtract, we're going to end up with the quantity b minus x squared minus x squared. Now we go to the second term, h1 squared minus h1 squared. That term's going to cancel out. And on the right side, we're left with a squared minus c squared. Now we now have two values of x that we could substitute into this equation. If we substitute in this value of x, c times the cosine of angle A, then that's going to give us a different equation that will entirely involve b's, lowercase a's and c's, as well as this cosine of angle A. Likewise, we could substitute this value of x in which case we would eliminate the x's again and be left with a quantity that involves b's, a's, c, and the cosine of angle C. And that's where the algebraic part of this comes into play. Now that we can kind of simplify that process a bit, if we go ahead and square this binomial, you're going to end up with a b squared minus 2bx plus x squared minus x squared equals a squared minus c squared. And you'll see in this case that the x squareds are going to cancel each other out. So ultimately what we're left with is b squared minus 2bx is equal to a squared minus c squared. And we're starting to kind of see the form of that Pythagorean law of cosine equation come into play. Okay, so I'm going to, at this point, we're going to leave that alone for just a moment. We know, substitute either of these in for x, and that's going to then produce some things that we'll look at in a moment. We're going to leave that where it is for now. Let's go back to our diagram for a minute. We're going to draw another height. In this case, I'm going to draw the height from point C to side AB. and we're going to call that h sub 2. And we know that h sub 2 divides the segment AB into two parts. We're going to refer to this part as y, which makes the other part c minus y. Remember, c was the length of the entire segment. Okay, so now we've got a couple of things we can do here. We have not, in any of these other two forms, we've looked at the cosine of angle A and the cosine of angle C. The one that we're missing, if we kind of examine our law of cosines, is the cosine of angle B. And that comes from this smaller right triangle here. So the cosine of angle B is equal to the adjacent y over the hypotenuse A. So A times the cosine of angle B is equal to y. Now, along the same lines as what we did on the last one, we can also look at the Pythagorean theorem that's going on here. In this case, we have, y squared plus h sub 2 squared is equal to a squared. And in the other right triangle, we have this quantity c minus y squared plus h sub 2 squared is equal to b squared. Now, if we follow the same steps that we did earlier on the other two triangles, then we can use the elimination method, subtracting the two equations like we did before. Go ahead and square that binomial and subtract. And we find that we're left with a similar form to what we have below. So the process from this point forward to prove all three forms of the law of cosines in the case of this acute triangle would be, in this case, to substitute this value of x or this value of x in place of x in the equation. And here we have a value of y that's in terms of cosine of angle B that we can substitute. And that part I'm going to go ahead and write out, but I'm not going to talk through it. So this is just substitution and then simplifying. So we can see in this case that all three forms then are proven through just substitution of these cosine expressions that we found for x and for y into this general form that's determined by using the Pythagorean theorems, and then just the processes of elimination and substitution to then get to the point where we have those three forms of the equation. Now, when it comes to the obtuse and the right angle case, especially in the case of the obtuse, you're going to find that it has a very similar process. You're going to start in much the same way that we did before by drawing two altitudes in, setting up some cosine functions, and then also your Pythagorean identities. And in this case, when it comes to drawing in your altitudes, you'll want to do that in two places. One of them is going to have to be outside the triangle, which is what we're going to see in this case. We're going to draw our altitude from point A down to this side segment CB. And we're also going to, we'll call that one H sub 1, and we'll draw a second altitude as well from angle C to side C. And that one you want to refer to as H sub 2. Now here again, it divides the side into parts, x and y, that are parts of the side. So let's refer to this part as x, which is going to make the other part of that c minus x. And as far as the exterior H sub 1, that exterior altitude, we're going to refer to this segment here as y. Now, keep in mind that y does not change the value of a. So we don't have an a minus y quantity. Rather, what we have is a quantity here, a plus y. So there's still two right angles present if you consider that red H sub 1 segment. We have the, let's call this point out here D for the moment so we can discuss it. But ultimately, we have a right triangle ADC that we can express some values out of. And we also have this right triangle ADB. So in the case of that H sub 1 segment, those are the two right triangles that you'll want to consider. When it comes to these two triangles created by H sub 2, it's going to be very similar to what you just did in the acute case. So I'm going to go ahead and do that acute case first, what was shown in the green, and we'll kind of fast forward through that process, and then we'll come back and talk about what happens in the case of this red H sub 1. Okay, so that part of it is very similar to what we did with the acute case. We end up with the same form of this equation that we talked about in the last one. We know that using this value of x is going to produce one of the versions of the law of cosines. If we use this value of x, this quantity in place of x, then that's going to give us the second form of our law of cosines, expressing something in the terms of cosine of angle B. Now let's look at what's going on then with that smaller right triangle outside. Okay, so for this, I want to look at the cosine of angle C here, which is actually angle ACD. So the cosine of angle ACD is equal to y over b, or b times the cosine of angle ACD is equal to y. Now it's important to realize that in the law of cosines, when they refer to c squared equals, etc., times the cosine of angle C, they're referring to angle ACB, the angle that's inside the triangle. Now we notice in this case that angle ACB, the one that we need to have expressed in our law of cosines, is a supplement to this angle that we've currently been working with. And if we think back to what we know about the supplements, or the cosine of supplementary angles, we know that they are opposites. That the cosine of the acute angle would be a positive number, and the cosine of an obtuse angle would be the opposite of that, a negative number. In this case, what's ultimately going to happen is, because I know that this interior angle, or not, this exterior angle ACD is expressed here, I can replace it with the opposite of the cosine of its supplement, which would be angle ACB. So that would mean that the opposite of b times the cosine of angle ACB is also equal to y. And that's going to then allow us to now write some more equations, and etc., to express an equation of that law of cosines that's going to involve that cosine of angle C. Because remember, this is the cosine of angle C in the original triangle ABC. Okay, so to get there, you're going to follow the same process as we used here, set up the Pythagorean identity or theorems, subtract, and so forth. And I'm going to do that part now, kind of in sped up form. Okay, and that's what we'd then end up with whenever we subtract those two equations. Now, I went ahead and multiplied this quantity out using that distributive property and subtracted the y squared term off. Now you'll notice here that unlike the other ones where we've had minus signs, this one now has a plus in it. But remember, the quantity that you're substituting for y has that negative in it, which is where that negative would then come from. So the rest of the process improving this law of cosines is very similar to then what we did at the end of the other proof with the acute case. Substituting in this value of x produces one form of the law. Substituting in this quantity for x creates another form or equation in that law. And then this one, of course, creates the third equation. And I'm going to allow you to go ahead and prove that on your own as part of the rest of your notes for this case number 2. Now, when it comes to the right triangle, it actually becomes simpler, because in that case, we're going to start with one side of the equation. So let's say we start with a squared plus b squared minus 2ab times the cosine of angle C. What we need to do then is use some simple substitution and properties of algebra to show that this entire quantity is equal to c squared, as the law states it should. Okay, so we're going back to the right triangle in this position and just writing down cosine values that we know based on right triangle trig ratios and what we know about the cosine of 90 degrees. So with that in mind, let's then go back to what we know here. This a squared plus b squared, etc. I'm going to leave the a squared plus b squared minus 2ab. But let's go ahead and substitute what we know about the cosine of angle C. Well, we've already said that that equals 0, which means this product all becomes 0, which means this is equal to a squared plus b squared. Now, the other thing that we know about this particular triangle, aside from these cosine functions, is that it is a right triangle. And we know that with any right triangle, the Pythagorean theorem holds true. So in this case, what's also considered known would be that a squared plus b squared is equal to c squared. So substituting in this position, we can see that in fact is true that this quantity is equal to c squared, which then proves one form of that law of cosines. The other two forms of that law of cosines are going to be formed in a very similar fashion, and I'm going to do that part kind of sped up so that you can just see what it looks like. Now, when we get to this point, we know that if we were to rearrange the terms in this Pythagorean theorem that we had written, if we were to subtract a squared on both sides, we would see that that's indeed equal to b squared. And the other form of the equation, where we start with b squared plus c squared, etc., that form would also hold the same general process that this one does, and I'm going to allow you to do that part as part of the rest of your notes.